One of the homework questions required a bit more tricks than I thought, but it's cool tricks. So thought that we'll go over them, how to get them for log n. It's still a question that you can do, but if you didn't do and you solved it in log square n, it's fine. But let's mention how to get it in log n. It requires a bit more trick, but I wanted to get myself prepared to put them in a nice way. So at the moment, I have two sorted arrays. I'm making it from geometric problems into just arrays, one-dimensional problem. I have one array A that has a set of keys, one array B that have a set of keys. I gave you all these keys, and I'm asking to find the median of the unified set in order log n. Asking you to find the median of the whole set in n log n. Now, if I ask it to do in order of, just to finish the definition, just a bit notations. If I give you some number x, and I'm asking what is the rank R of x in A, the rank of x in this A is where does it stand if I sort the numbers. Rank of 2 in A is 1, rank of 3 is 2, rank of 5 is 3, and so on. And rank of 19 in A will be 7. Rank of x in B, same way. Rank of 10 is 5, but I can also ask what would be the rank of 7 in B. I can also ask what would be the rank of 7 in B, even though 7 is not a key, and I'm saying how many keys do I have that are smaller than 7 plus 1. I imagine for a moment that it's in the set and count what is its rank now. Okay, so I can ask what is the rank of a value, that is how many numbers are smaller than it. I can ask what is the rank of in A only. I can ask what is the rank in B only of any number in the world, as well as what is the rank of the same key x, but in the unified set. If I had linear time to squish the two arrays with each other, then I can ask how many elements in both A and B are smaller than some value x. So the rank of x would be the rank of 10 in the unified set would be 5 elements in B itself plus 4 elements. In how many elements are smaller than 10 happens to be also 4. So it will be 4 by 4. Okay, everybody is cool with this notation. They are the rank of x in A only, or in B only, or in any unified B. My advisor really like to use the meaning of respectively, meaning that if you have a list, then this refers to the first number, this refers to the second, this refers to the third. Familiar with this? Not the resp point. Okay, now I'm looking for a median. I'm looking for an R of the median when I find it in A union B should be, how many do I have? 7 plus 7, 14. 14 divided by 2 will make it 7. That's what will be when I find the median. Warm up. Log square of A. That's kind of like what we did when we find the line that when we found if two polygons cross each other, two convex polygons cross each other. Right. It's even simpler in one dimension. I will have log n probes in A, for example. I'll pick a number, say the median of A, 8, ask what is the rank of A in B, and now it tells me whether the total number of 8 in A and in B is smaller or larger than what I'm looking for, which will tell me you need to go right or left in A, and when you narrowed A enough, you can move if you have some gap in B. You can do another log. But every time that you are gambling on an element of A, you're performing binary search in, every time that you're gambling on an element of B, you're performing log n probes, binary search, find essentially in A of these numbers that you're meditating on to know what is its rank over here. When we asked if two polygons intersect, two convex polygons intersect, the algorithm was gamble on a line, find where is this line in the other polygon, which will take you log n time, and now we're using data about the edges that this line crosses, you know whether you need to go left or right. And that gives you the log square n, because the outer loop is log n times, and the inner loop is for every element, every candidate that the outer loop generates, I need log n probes in the other array to know what is the rank in the other array. So let's see how to do it in only log n. Everybody cool with this problem? That's a bit auxiliary to our work. It's a very cool algorithm, and it is used lots of times, but I will not say that's a mainstream, but the idea that we played with in the intersection of polygons are really, really crucial. So the log square n, everybody needs to. Okay. Back into our region. So I want to draw the uncertainty region. The uncertainty region will be where do I know that A or B must lie? And to start with, I have no clue, so my uncertainty is just the whole arrays. But as I progress, I will limit the uncertainty at each step. Like, you know, the uncertainty in binary search, you're just taking the middle element and you're saying the uncertainty has been shrinked into either the right half or the left half in just normal binary search. Here, lives are a bit strange, a bit more strange. Anyhow, I'm looking for an element whose rank in A union B is 7. And right now, I'll think about the two medians. In general, at each iteration, I'll have the mid that I'll consider, one from A, one from B. So let's take the median of A. Let's take the median of A. I want to change the numbers a bit, so let me make these numbers, just these four. So 2, 4, 6, 18, 110, 120, 140. So the median of A is 7, the median of B is 18, and assume at the moment that the median of A is smaller than the median of B. Otherwise, I'll just switch rules. And I'm also counting and I want to ask what is the rank of A at A plus what is the rank of B at B. Look at this number, and in our case, this number is larger than the median of A union B, the combined median. Given that, and now meditate on 4 half arrays. Meditate on these 4 half arrays. I split B, or I split the uncertainty of B into 2 halves. I split the uncertainty of A into 2 halves. I split the uncertainty of B into 2 halves. I split the uncertainty of A into 2 halves by picking the median. So we have 4 halves of an array. Can you show me one of these halves that the combined median is not in there?
Could you repeat that?
Out of these 4 halves, that would be 1 half with the median. Let's say this will be the other half, another one, and another one. 4 halves over an array. Either one of these 4 halves that are definitely not equal to the median. Yes?
The right half of B is definitely not.
Correct answer. The right half of B, the median is not there. Why? Because this guy is already larger than this guy. How many elements are smaller than 110? Well, I'm not sure how many elements are smaller than the 110 in A. I mean, I'll need to spend log n time to do it. In this case, it's a lot of them. But even if I just think about all the elements that I'm sure that are smaller than this guy, first, why did we pick B? We picked B because because its median is larger than the median of the other array. Which means that if I'll ask how many elements, in this case, what is the rank of 18 in A? The ranking of 18 in B, we know. That's how we picked it, to be the median. And any element that I pick from B, I know what is its rank in B. What is the rank of the median, the largest of the two? What is the median of the largest of the two with respect to A? I don't know exactly. Yeah.
You know, it's at least one more than the rank of 7.
Exactly. I don't know what is the number exactly, but I know that smaller than it are definitely all the elements that are smaller than its own median, maybe a few more. So its rank is too large for me. That is, that 118 in the combined list is either in the largest half or even too large. there is too many elements that I'm sure that are smaller than 18. Namely, I'm absolutely sure that smaller than this guy are all the elements here are all smaller than 18. All the elements here are smaller than 18. Why? Because their median is smaller than 18. And maybe a few here. So the rank of 18 at A is large or equal than the global median, then the global 7, which helps me in which way? It tells me that now my uncertainty region of that in B, anybody in this region should not be counted. So my uncertainty region from now on just looks at this region. And the next element that I'll pick will be the median of these guys. So my next element would be in the uncertainty of B, just pick the middle one, say, pick 4. Now, what is its rank in A? 2. What is the rank of the median at A? 7. Which one is smaller? 4 is smaller than 7. The rank of this guy plus the rank of this guy, is it smaller or larger than 7? It's smaller than 7. 4 plus 2 is smaller than 7, implying that everybody that is smaller than the small guy, in this case. At each moment you are asking, who is larger? This, and are the sum larger than the median or smaller than the median? In every case, you are getting rid of one of the 4 quadrants. Notice that when I'm limiting my uncertainty region, I don't change the rank. The rank of every element is the same. But when I pick the middle guy, what you know from binary search as a mid, it will be the mid of the uncertainty search. So each operation, either A shrinks by half or B shrinks by half, and in some cases you can shrink both of them by half. Okay, so how many iterations do I have? At most log n for B, at most log n for A. I don't know ahead of time if the one that will shrink would be either A or B. No clue. Depending on how numbers are distributed, but at each operation, you are getting rid of at least half of the existing arrays. So for the total number of halving steps that you might have is not more than log n plus log n. Didn't ask. People on Zoom can you hear me? Okay, thanks. Yeah, let's continue with graph connectivity. Unless there are homework 2 questions.
Question. For 7a.
We might be.
So you're counting all the intersections of circles,
Mm-hmm.
and then finding the depth of all those intersections. So how many circles?
That's a question when they intersect or they don't. Where they do intersect, yes.
Yeah. And they have to find how many circles contain the intersection.
Yeah.
In log squared or n squared log n time.
Yes.
So I figured out how to do it for the 7b.
By the way, if you're doing it in the next section, you don't need to solve. The next section asks the same, to give the same output, but in only you're replacing the n squared by k, by how many intersections there are. So if you are getting this one correctly, then you don't need to solve B. But I wanted you to think about B also, because it's completely different idea. It doesn't use line sweep directly.
Okay. So if I answer B, then I don't have to answer A.
I think, I don't remember A exactly, but it sounds like. And if you are, I mean, every question is built like a few sections, and if you, so you, even if you don't answer everything, there will be things that you'll ask. But Yeah. So I don't remember by heart, but if I remember correctly, then the last section is the one that includes everything. Is the one that is the hardest, and if you solve this one, then everything else is included. Okay, let's continue with connectivity. So we talked about graphs when a graph is connected. Here is graph embedding, not extremely crucial in this course. Stefan Koborov, our neighbor from his office over there, has a huge amount of results about how to embed graphs, or which is planar or close to being planar, or nice in one way or another. He became one of the top experts in the world in information visualization, coming up with background about graph embedding. Just making sure that the camera is happy. Yeah. Okay. So the graph is an abstract thing, vertices and edges. I need to draw it somehow, either in 2 dimensions, in 3 dimensions, and for the same graph, there could be plenty different embedding. Okay. Little nuance that it's fine if you are getting confused, but if you do see it, know the difference between a plane graph versus a planar graph. Planar graph is an abstract creature that consists of edges and vertices. Plane graph is just a shorthand of here is a graph and here is how it is drawn in the, how it's rendered in the plane in a way that no 2 edges cross each other. Edges might meet at a vertex, but they are not allowed to cross each other. If you cannot draw the graph, embed the graph in any way without crossing, then it's not a planar graph. So plane graph, once again, it's a shorthand of a graph plus its drawing. And there are a lot of interesting questions, like if I show you a graph, how much time does it take for you to validate if this graph is planar or not? And the answer is that it can be done in linear time, but far from being trivial. A few other results is, here is one planar graph, but its drawing, its embedding is not planar. Right? You see 2 edges that do cross. Now, how do I know that these 2 graphs are the same? Because look at the neighbors of A in this graph, which are B, B, and C, and these are the same neighbors in this graph. By the way, this graph is a clique of size 4. Everybody is connected to everybody, by the way. But it's not the general case. Here is another way to render this graph. Now I don't have any crossings, but you see one edge that is very ugly, not straight. If you think about it as a way to put information on a map, say to put train lines on the map, you probably want to say that this is not desired. Here is an embedding of the very same graph, but now every edge is a straight line segment. A pretty cool theorem, again not trivial, is that if you can render the graph, embed the graph with curvy edges like this, but without crossing, so if you can do it for a graph and it's planar graph, then there is a different embedding where all the edges are straight line. Now, here you see 4 faces of this graph, right? One of them is the outer face, remember? What does it mean for 2 points to be in a face? 2 points are in a face if I can start from one point and go to the other and I don't have to cross any edges. These 2 points are planar, these 2 points are planar, and so on. These 2 points are in one face, the other one was in another face, and so on. How many faces do you see right here? There are 4 faces. 3 in normal one and one that we call the outer face that goes to infinity. And you can ask, can I draw it when this, can I render this graph when this face is the outer face? And yes, and you need an orange for it. What you're doing is you are taking this graph and draw it on an orange. And then you're peeling the orange, but the point that you start peeling is inside this face. So when you finish flattening the skin of the orange, it will turn out that this was the outer face. And think about it, put 4 points on an orange, connect them by rubber bands, and convince yourself that if you allow the edges to deform and stretch, then each one of the faces might be the outer one. Okay? So, and if I give you a graph, it doesn't matter how I render it, it will always have the same number of faces. Triangulation, just a straight line planar graph, where every face is a triangle, has 3 edges. And when you show me a set of points, out of all there are exponentially many different types of triangulation. But triangulation is really important. It's important if you want to say these points come from a surface that I'm going to render in my graphics display, or they are the skin of something that I send to my 3D printer, or this is a piece of metal where I'm putting some heat to one point, and I want to see how the heat dissipates inside this part. And since this part is complicated, I'll divide the part into small parts, where at each part I'll just ask how one heated edge of a triangle affects this time the other 2 edges, and let this one dissipate. So there are definitely triangulations that are better than others for the same part. And the same way, if you are thinking about an object with 3D, then it's not triangulation, it's tetrahornization. Dividing it into small pyramids, each with 4 points and 4 triangles, and that would be just a 3D equivalent. So there are a lot of triangulations depending on your applications. Some are better than the other, but there is one that is the universal answer, 42. No matter what you ask, that will be your answer when it's asked, what is good triangulation? And 42 here will be the Lanois triangulation that we'll spend lots of time in this course. See it and its application. So here is a pretty boring definition of the Lanois triangulation. The Lanois triangulation would have the property that if I look at one triangle, every triangle defines a circle that goes through its vertices. Every triangle in the triangulation, every 3 points, of course, it's a bit, let's say, 3 non-collinear points, they define one circle. How do I know that this triangulation is the Lanois triangulation? Its definition means take every triangle, take the circle that its 3 vertices defines. If it's the Lanois triangulation, then you don't allow any other vertex to be in this circle. Once again, that's the Lanois triangulation, and what's so special about it, except that it's very good for multiple operation, is that it's very much related to Voronoi diagram. It's a dual graph of the Voronoi diagram. If you know the Voronoi diagram, then you know the Lanois triangulation and vice versa. The center of the circle is exactly a vertex of the Voronoi diagram. It's a point that is equal distance from this point, from this point, from this point, and every other point is too far. If you don't remember what's Voronoi diagram from the first meeting, that's fine. You spend a lot of time. In Voronoi diagram, just to convince you that this property of empty circles have something nice about it, is so I have a set of 4 points, A, B, C, D, and these 4 points defines exactly 2 triangulations. That's one, that's another one. What's the difference between these triangulation? Just that this edge, the middle edge, here it connects C and A, here it connects D and B. Which one of them is the Lanois one? Let's check our property of empty circles with this triangulation. Making an attempt to draw a circle, it will be a pretty large one, and definitely A lies somewhere inside. So this is not the Lanois triangulation. This is the circle that I'll draw for these 3 guys. Will do the job for me. At least it's evidence. Of course, it's subjective or depending on applications, but the claim is that for most applications, this is a pretty bad triangulation. It's very hard to know if I'm hitting this side. This side is very far away, for example. If you're building it and there is some physical properties to it, they are not concentrated in the same region, but it's like very stretched and very thin. We don't like very sharp and very thin triangles in this context. We prefer triangles where all the angles are large, at least as large as they could be. We prefer triangles that their aspect ratio, area versus diameters, are small, they are compact. It's a kind of a universal property that makes good triangulation. Do you see the font? Although too far. Okay, now or still? That's what I want to do as much as I want to do in real time. So I want to show you here 2 graphs. Just to, it's promo to other things that we want to handle. There was a question?
So I had a question about that. So if you move D closer to the CA line segment, would it no longer be a, forgot what it's called?
Delanoy.
Yeah, Delanoy.
Name of a Russian mathematician. If I move, it's an empty circle triangulation. Usually there is only one such circle, one such triangulation.
What does that mean?
Sorry?
What does that mean?
That if you determine a set of points, in general, there will only be a single Delanoy triangulation. The only exceptions would be if I have 4 points, if I have a circle with 4 points on it, then no matter how you triangulate these 4 points, I have the empty circle property.
Yeah.
But let's play a bit, give you a form of where we are going with it. I have a set of sides. So it's really looking good. Let me try to increase it a bit. So you have the set of hospitals or sites over here. H is 1, C is 1, F is 1. And I can look at their Delanoy triangulation, where you see in blue. I can also look at the Voronoi diagram that you see in red. What is a Voronoi diagram? Just to remind you, Voronoi diagram is dividing the plane into regions so that 2 points are in one region if they have the same site to both these points. They have the same closest hospital. The points A, B, H, etc. are hospitals. They want to divide the plane into hospitals, into a region so that the nearest hospital in a region is the same. Here is one Voronoi cell, the hospital B here in the middle. Every point in this cell is closer to B, more closer than it's closer to C. What does it mean to be on an edge of the Voronoi diagram? It means that you are equidistant to 2 hospitals. But that's an edge that separates 2 faces. What does it mean to be on a vertex of the Voronoi diagram? It means that you are equidistant to 3 sides. And oh, by the way, I should have said it for the 2. When I'm on this edge, my distance to B equals to my distance to C, but my distance to H is much larger. My distance to F is much larger. That is, C and B are my 2 nearest hospitals. Similarly, being on the vertex of the Voronoi diagram, then you have 3 equidistant vertices for this vertex, and these are your nearest site, which means that if you take this point and start drawing a circle if I start drawing a circle from this point, it will hit F and E and D at the very same time, and it will not hit anybody else before because they are the nearest neighbors. So that's a great example of what is a dual graph or a planar graph. When I have one graph, I can describe the dual of this graph. The dual of a graph, G, denoted, probably too small, denoted by G hat or V hat and E hat. What do I do to create a dual? I look at the original graph, say the Voronoi diagram, and I'll place a vertex, say the side, and each a vertex of the dual at each side, and I'll connect 2 sides by an edge in the dual if the 2 faces that they sit on are neighboring, that they share an edge. So let's have a smaller example to understand what I'm talking about. I'll ignore the outer face. So you see 3 faces over here. To create the dual graph of this graph, you see that it is a graph, right? It has 4 vertices. It has 4 vertices, 3 plus 1 edges, yada yada. To create the dual of this graph, I'll put a vertex in each face. And if two faces share an edge, I'll connect them by an edge of the dual. These two guys share an edge. The two faces are neighboring. Connect. So that would be the dual. It looks completely abstract and out of context right now. We'll see an application coming up very soon. It's okay if you didn't entirely understood all the properties of the primal and the dual. But there's a lot of cute properties. If I take the dual and compute the dual of the dual, what do I get? The graph that I started with. If one is planar, the other one is planar. It's quite useful in a lot of tricks. But it's fine if you didn't get it. Yeah?
The edges that are like going outwards, those are not showing.
So again?
The edges that are like going to infinity, those don't cross two faces.
Of the dual? You mean of the Delanoy triangulation? So this face with infinity, I picked a point H. This face of infinity, I picked a point A. And I connect them by a segment if the two faces that I picked are neighboring to each other. It's fine if the segment leaves the union of these two faces for a bit. That's not a big deal. As long as the two faces are neighboring to each other, like this state and this state share a border, connect them by an edge. This state and this state share a border, connect them by an edge. Okay, it's a promo, we'll get back to it much more. Let's talk about Euler formula. Very, very cool. Euler formula tells you the following. Look at the planar graph, and I'll assume that the planar graph is connected. It's not two graph with nothing between. It's between any two vertices. I should be able to walk along edges and go from one vertex to another. It's connected. And I'll assume that I don't have parallel edges, two edges that connect the same pair of vertices u to v. I'll just count them as one edge. Everybody understand what are parallel edges? If I have two edges in my graph between these two vertices, I just connect them as one edge. Get rid of one of them. Okay, so Euler formula tells you the following. Count this graph, this example. It has 6 vertices, 1, 2, 3, 4, 5, 6. It has 3 faces. How come? 1, 2, 3 outside. And it has 7 edges. 1, 2, 3, another 4 over there. Euler formula tells you as long as you are drawing this graph on the plane, then there is a very simple formula that tells you how these 3 numbers relate to each other. Take the number of vertices, add to it the number of faces, and subtract the number of edges. It will be 2. How many of you have heard about genus of a shape? Genus, you can have it in different terms. In topology, it's like how many holes you have in a shape, kind of. It just means that these 2 will be switched by a different number if you draw it on a bagel, for example. Something with holes on the toes. Then it's actually a constant, but it's different constant depending on these shapes that you have in mind. Anyway, let's stay in the plane, Euclidean plane, and let's prove this formula. V plus f minus e will be equal to. How am I going to prove this formula? I need a little lemma that says that in any tree, tree in graphs just means it doesn't have cycles and it is connected. So in any tree, I'm looking at the number of vertices and I'm looking at the number of edges. Number of vertices, number of edges. Example, here is a tree, 2 vertices, 1 edge. I want to tell you that it's always the case, that V equals E minus 1 in a tree. And you can easily convince yourself by induction. Think about lots of other things that are connected into this tree. There is a lot and lot of other structures that are connected by the tree. I still want to tell you that it's true. Why? Because if you're picking a leaf, how do I know that I can pick a leaf in this graph? Because, and we'll use this similar trick very soon, how do I know that I can pick a leaf? That there is leaves inside it. Not every graph has leaves, for example. This one doesn't. But there is a cycle. A tree doesn't have any cycles. By definition, tree is a connected graph which doesn't have any cycles. So I can pick a leaf, I'll delete this vertex, and I'll delete this edge. I decreased V by 1, I decreased E by 1. Check, yeah.
Isn't it
Plus 1, number of vertices, yeah, plus 1. Correct. Again, proof by example is 1 plus 1 equals 2. Okay. Now here is my planar graph. Here is my planar graph. And the first thing that I'm doing is picking every edge that closes a cycle, pick an edge that closes a cycle, and remove it. If there is still a cycle, pick any edge from the cycle, remove it. You are not destroying the connectivity of this graph, because you are only eliminating an edge once you see that it is on a cycle. Cycle is a graph, not geometric. So here is one such cycle. So I opened it over here, removed one of these edges. Here is this triangle. I removed this edge over here. Is Euler formula holds at this moment, after I did all these deletions? Kind of, yes, because if you are using our corrected formula, thanks for the correction, you're using our corrected formula, what is f? In a tree, f is 1. Any 2 points are connected, 1/5. What does it mean? That the number of vertices plus 1 minus the number of edges should be equal to. If you believe this formula over there, then yeah, believe it, after the correction. Now I'll put this edge back. Now, since I already have a cycle, every edge that I'm putting back, let's see an example, I'm only adding an edge between 2 vertices that are already connected. What did I do to the number of faces? I took the outer face and I split it into 2 faces, increase the number of faces by 1. That is, I added 1 edge and I added 1 to the number of faces. So if it was true before, it's true now. Let's have another such edge. I took this edge and divided it into 2, again adding 1 face and adding 1 edge. So the formula is true even if I'm putting back all the edges that I deleted. Okay. And if you're playing a bit with this formula, there is a lot of conclusions that we can scan through it for the sake of time. That essentially, if I know how many vertices a planar graph has, then the number of edges and the number of faces are all linear, or bounded by linear. If you're saying it has n edges and it has order n faces, then it has order n vertices, edges and order n faces. At most order n, maybe less. You're playing with it a bit more, and you think about the half edges instead of edges. Do try to remember what is a DCL. Let's think that it's a triangulation. Every triangulation uses exactly 3 half edges. Now the number of edges that I used is doubled, so because it's half edges instead of just edges. So the original number, I had that v plus f minus e equals 2, implying that the number of faces, every face in a triangulation uses exactly 3 edges. The outer one uses a few more, but that's why it's small or equal. So the number of faces cannot be take all the half edges that you have. Each face uses 3 of them at least. Some faces uses more. So the number of faces is limited by the twice the number of edges, 2 because I used half edges, divided by 3 because the smallest face that I can have is a triangle. Maybe it has 4, maybe 5 edges along it. So that's a bound on the number of faces. Throwing it back into Euler formula and cracking up the numbers, we are getting that the number of edges, therefore, that the number of edges that's for is only 3 times the number of vertices. Now the faces are not there. That's in a triangulation, it's slightly different. It's even better. And if you're cracking up the numbers a bit more, you're getting that, let's sum up the degree of every vertex. For every vertex, I'll sum up the number of neighbors. I want to show you a graph. Let's say this bipartite graph, everybody is connected to everybody, the degree can be as large as they want. And the average degree can be as large as they want. In planar graph, life are much better. The total number of degrees is only linear, is only 6 times the number of vertices. So most vertices have degree of 6. Think about it as I only talk to somebody that is near B and I'm designing some graph, but it's planar. The average degree is about 6 per vertex. It doesn't mean that I cannot draw something that is much more complicated, and now this vertex at the middle is connected to a lot of other vertices. But if you're asking what is the average degree of all the vertices, it's about 6. And that's pretty cool, and it has a lot of application, like the assigning frequencies to transmission, if these nodes represent wireless receivers, transmitters, and so on. So it's really, really useful result. But the take-home messages from all of it is that if it's planar graph, once I told you what the number of faces, the number of edges, number of vertices are all within a constant. As opposed to this bipartite graph where the number of edges is quadratic in the number of vertices. Out gallery problems that we discussed as applications to the ILP. I want to give some beautiful, beautiful results about number of guards that I need to guard a simple polygon. So, just going over the same definitions that we saw already, I'm having a polygon, simple polygon, meaning it doesn't have holes, and it doesn't have creatures like this. That's not a simple polygon. Okay, so, by the way, that was the answer to your question about going a polygon that all your terms are right terms, but it's not convex. You can massage it a bit, but that would be an example to one of the homework 1 questions of polygons that is your only turning rate, but it's not convex. But it's not simple polygon. There is not I don't know what's the inner side and the outer side. Back to our slide. Normal polygons, the buildings in the house, 2 points seize each other, PQ, if the segment between them lies fully inside the polygon. There are no walls that occludes one from the other. So P sees Q. I can ask what is the visibility region of a point P. Visibility region of a point P is all the points that P sees. The shaded area are all the points that P sees. And that's what we call visibility cut, because it's exactly the area between what P sees or don't see. Or alternatively, put a lamp over here, then here you're in the shadow of this lamp, you are illuminated by this lamp. And that's exactly the line of where the light becomes shadow. Okay, so now you know what is a visibility region. And the question is, given a polygon P, what is the minimum number of guards that require to guard P? As any other interesting question, it's NP hard. To find the optimum number, there are lots of approximations, but we will still be able to give some bounds to this number. Just quick observation, discussed it last meeting. If I have convex polygon, one guard will do. One guard will do. Star-shaped polygon, by definition, is exactly a polygon that there is some point, maybe not every point, but there is some point that sees the whole polygon. There is actually an area called the core of the star-shaped polygon. And one of your questions in homework 3 would be, given a polygon, tell me in linear time whether it's star-shaped or not. It's a cute question. Again, given a polygon, tell me in linear time whether it's star-shaped. It will be in the next homework. So that's a star shape, that's not a star shape. Yes, sir?
Does a star-shaped polygon have to be not convex?
No. Convex is star shaped. But not the other way around. So, easy upper bound. I want to convince you that I can always guard this polygon with n vertices and n edges, of course. It's simple polygon, so the number of vertices is the number of edges. And I want to convince you that I don't need more than n minus 2 guards. How? Why? Because I want to show you that this polygon can be triangulated. I can partition it into triangles. And I'll use no more than n minus 2 triangles. Exactly n minus 2 triangles will be the answer. And inside every triangle, place a guard. Cool. So I owe you why it is n minus 2 triangulate, why it consists of n minus 2 triangles of the polygon. And any point inside each one of these triangles will do. Okay, so theorem. Any simple polygon with n vertices has a triangulation with n minus 2 guards. Has a triangulation with n minus 2 triangles. Example, n equals 3. 3 minus 2, I can prove it, equal 1. There is one triangle. N equal 4, it is 2 triangles out of. Let's prove it in general. So to prove it in general, I want to speak about diagonals in the polygon. Diagonal in the polygon P is a line segment that starts at a vertex, ends at a vertex. It doesn't connect two neighbors that are adjacent to each other. So an edge of the polygon doesn't, I don't call it diagonal. It has to connect two vertices that are not adjacent. It has to be fully inside the polygon. I need to start and end at vertices. So this is not a diagonal, but this one is. Connect to vertices, then it's fully inside the polygon. This one is. So any polygon with n larger than 3 vertices has a diagonal. I can find at least one diagonal inside this polygon. And it's surprisingly tricky, actually, to prove it. So let's do it. It sounds somehow obvious, but it's less so. So how do I prove that it has one such diagonal? Look at the leftmost vertex, V. I write my polygon and I'm looking at the leftmost vertex V. And now I'm looking at who are the neighbors of V on the polygon, making it U and W. First attempt is try to connect U to W. Maybe this code is already inside the polygon and you're done. Because then you found an ear. Ear would be a piece of the polygon, and ear would be any piece of the polygon, like these two edges, that you can connect by an edge, and by connecting by an edge, you removed this one triangle from the polygon. We will have a formal definition coming up. So I'm attempting to connect U to W. And if I succeeded, then I can prove my theorem by induction. But if it was true for any polygon that has fewer vertices than it's true now, because I just get rid of one such. And I can keep doing it until I break it into triangles. So here is the harder part. Assuming that U and W don't see each other, if I'll attempt to connect them via diagonal, this diagonal exits my polygon. And now I'm looking at all, it means that the boundary of the polygon has some pieces that crosses this line from U to V, right? It means that there should be some piece of the polygon besides V and its two edges. There are more pieces of the polygon to the left of this line. Otherwise U could have seen V. Why doesn't U see W? Sorry, why doesn't U see W? There are some pieces of the polygon that obscure them, and these pieces cannot be the two edges that comes from U to W. By definition, they are straight line. There is some other part. So I'll take my stick and move it parallel to itself, until I hit the leftmost vertex that is not V. That is not V. So from UW, move to the left until you find the very last vertex. And I claim that this vertex, the leftmost vertex in this set, must seize V. Why? Because if there was something else that separates them, then there would be a point that is more to the left than what I've shown. Again, I continue with my stick, with this stick line through it, until I got to the leftmost vertex that is still to the right of B. Okay, so there is such an edge. There is such a diagonal. Okay. Which means that any simple polygon with n vertices has a triangulation that consists of n minus 3, that's what we are going to prove, consists of n minus 3 diagonals and n minus 2 triangles. The triangle is an example of a polygon that you need no more diagonals to add. For the later on, then there are 2 triangles and 1 chord. Poof, induction on it. Triangle, it holds. Any polygon that has a collective 3 triangles, this formula works for it. Now let's take now you have proven this claim, just to remind you how induction works. Assume that I have proven it for all the polygons that have 3 vertices, Now I want to show you how I can prove it for every polygon that has 4 vertices, based on the fact that for every 3 it's checked. Once I'm done proving it for all the polygon with 4 vertices, I'll show you how every polygon with 5 vertices, you can solve it using what you already know of polygons with 4, and so on. How we are moving from the proof of n to the proof of n plus 1. So here is a polygon with n plus 1 many vertices. With a polygon with n plus 1, and that's the first polygon with so many vertices that I see. So far I've seen polygons with n or less triangles, but every polygon with n or less vertices, my proof correct. I validated my proof for every polygon with n or less vertices. Here is the first time that I see a polygon with exactly n plus 1 many vertices. What does the previous theorem tells us? It says there is some diagonal. I'm sure that you all thought about it. If I want to prove it by induction, I want to divide it into smaller polygons. There is one diagonal. Actually, there is lots of them, but there is one diagonal that I can find. Its existence is guaranteed by the previous theorem. This left triangle has n1 many vertices. The right triangle has n2 many vertices. And what do I know about n1 plus n2? It's almost equal to n, to the number of vertices of the original polygon, except that these 2 vertices were counted twice. This one was counted twice, one from the right side, one from the left side. The same goes for this one. Okay, so n equals n1 plus n2 minus 2. That's the number of original vertices. What's important is that each one of these new polygons has less than n many vertices. The left side and the right side has fewer than n, so I can apply the induction assumption for it. For every polygon with n vertices, I can triangulate it using what the formula tells me. Formula told me that the left triangle has, that the left triangle with the n1 has n1 minus 2 many triangles. The right triangle, everything to the right of this line, has n2 minus 2, again from the induction, because they have less than n. Sum up these 2 numbers. How many triangles do you get at the end? N minus 2. When the smoke here clears up. That's the number of triangles that you have. How many diagonals that you have? We said that every triangulation has triangulation with n minus 3. So it's n minus 3 plus n2 minus 3 plus 1 that I added because they shared one diagonal. It will end up to the right number. Okay, so we proved the theorem. Let's at least start the exciting part. Questions about it? Okay, so what I'm going to prove to you, and it's really one of the little jumps that are in computation, in the very introduction of computational geometry. What I'm going to prove to you is that I can look at the vertices of the polygon where they are already, after it was triangulated. I just convinced you that I can triangulate it. We don't worry about the running time of the algorithm. I can triangulate this polygon. What is the triangulation? By the way, I didn't say it. Triangulation would mean I subdivide it into faces, and every face has exactly 3 edges. That's it, triangulation. So the theorem wants to show that you can now look at all these triangles, and you have 3 colors. Some of you are familiar with 6 colors, 4 colors, something about painting maps. That's a similar theorem. It wants to show, look at this polygon, and you have 3 colors. Look at all these triangles. I can assign a color to each vertex. Some of these vertices might be shared by many triangles, by the way. I can still assign a color to each vertex, such that for every triangle in the triangulation, you'll see one candidate of each color. Brown, purple, green for this triangle. Purple, green, brown for this triangle, and so on. Okay, I want to prove to you that I can paint these vertices in a way that every triangle has exactly one candidate of each color. What I'm not telling you is how many greens, how many yellow, how many red I have. But that's pretty cute. So I didn't tell you how many green, how many blue, how many I have. I don't say that there are exactly the same number. Quite possible that I have many more blues than greens. I don't know. Nevertheless, when I sum up the number of green plus number of blue plus number of red, I'm getting exactly n. So one of these three numbers should be either n over 3 or even smaller. Because if you're summing three numbers, all of them are larger than n over 3, summing three numbers and all are larger than n over 3, you're getting a number that is larger than n. Color, every vertex is monochromatic. So one of these three sets of vertices has at most n over 3 vertices, and I pick this set, and that's exactly where I put my guard. And since from this set I have a candidate in each triangle, I guarded the whole polygon. So for simple polygon, I never need more than n over 3 many vertices. Okay, so what was left for next meeting is to prove this theorem. Why do I need only n over 3? And the proof is used years, a bit simulation to Van Gogh. What we'll do is basically say, I can remove an ear, a triangle that has two edges of the original polygon. I have to prove to you that there is such a triangle that has two edges for the original polygon. And I'll put colors of this or smaller polygon, and now I'll put this ear back. And this ear, what does it have? What this triangle has? It is one purple triangle, one purple vertex, one brown vertex. So which color will I pick for the one that was removed and now putting back? There is always the third color that this vertex can pick. So I'll erase the polygon until it's becoming just a triangle, color this triangle, and then put the triangles once at a time. And each time that I'm adding a triangle, I'll show you that I can still keep colors so that this invariant maintains. Good. Modulo this theorem that we need to prove. Any questions? Good. Thank you.